Hello and welcome to Lecture 5. This is where things get complex, so to speak, because we're going to be dealing with AC currents for inductors and capacitors. So this is all review of stuff that you did in second year and a little bit of stuff that you did in first year. Review of complex numbers. So we'll need this to make life easy for AC circuits involving inductors and capacitors. Remember that Euler's identity is e to the I theta cos is equal to cos of theta plus I times sine of theta, where I is the square root of -1, the 1 kind of for imaginary numbers. Many circuits textbooks use J as the root of -1 and keep I for an AC current. Our book does things a little bit different because it's a physics approach to electronics, so it keeps the notation that's used in most of physics, which is that I is the root of -1. In programming is another area that you'll see J used for the root of -1, so just be aware that sometimes you'll see J, sometimes you'll see I. Most of the time in circuits, if you look online, you'll see that they use J for this. Don't be thrown off. Now, I encourage the curious student to go and try to prove Euler's identity using the Maclaurin series for cos and sine. It's a lot of fun to do. If you've never done that, then give it a shot. You'll be quite pleased when you figure it out. Cartesian form of a complex number is z is equal to x plus I y. So y is the imaginary part, x is the real part. Polar form, z is r e to the I theta. R is the magnitude now, and theta is called the phase. You can convert between these, so x is r cos theta, y is r sine theta. Just draw out the triangle that this represents, and it's exactly the same as converting from polar coordinates to Cartesian coordinates. And similarly, r is the root of x squared plus y squared, while theta is the arctan of y over x. Be careful with theta because arctan's range is not as large as you'd like it to be. So the information is lost about whether it was actually the y or the x that was positive, so you have to go back to the information that you had about y or x to decide whether you need to add a pi or a 180 degrees to the results you got from the arctan. Cartesian form is the most useful if you're going to be adding and subtracting complex numbers. Polar form, on the other hand, is best for multiplying, dividing, and taking exponents. You also need to know complex conjugate, so this is shown with a bar over the complex number you're taking the conjugate of, and all you do is you multiply the imaginary part by -1. So if it was positive, you make it negative. If it was negative, you make it positive. Multiplying a complex number by its complex conjugate is what replaces taking the square of a complex number a lot of the time. So if you wanted to find the magnitude of a number, then what you have to do is take the square root of the complex number multiplied by its complex conjugate. This is what causes the imaginary parts to go away, and you're left with x squared plus y squared, which is r squared. Now, convention, I is usually placed between values and variables. It's kind of somewhere in between that in order of priority, so you'd write things like 2i, but if you have an i then a variable, then you'd write ix. If you have all three, it'd be 2ix, but not usually something like I2, xi, x2i, except maybe in an intermediate step of a calculus. Complex impedance formalism for AC circuits, frequency filters. All right, a time-varying voltage signal you can write as an amplitude of voltage times a cosine of omega t. Omega would be the angular frequency, and you can express this as a complex number using Euler's identity as the real part of this complex exponential. So now we're imagining there's also a phase constant here. The phase is everything in the argument of cos. The phase constant is just this extra part there. So the voltage then is the real part of this. This is much more convenient than dealing with trig functions, so these exponentials are a lot easier to deal with a lot of the time. And so we'll usually just write it as a complex exponential. So we'll say the voltage is equal to this. What we really mean is the voltage is the real part of this. And remember to take that real part into consideration if you want to find out what the instantaneous voltage is at any point. Now, the voltage phasor would be just this thing on the right. So sometimes you'll call this the voltage phasor if you want to distinguish between it and the actual voltage. Sometimes we'll just call this the voltage and understand that really it's the voltage phasor and the voltage is the real part of this. If you look online, then you'll see the voltage phasor is often defined as this without the time dependence written either. So we just kind of imply the time dependence, and we write that this is the voltage. So the voltage is V naught e to the I phi, or V naught at an angle of phi, and it's implied that it's time varying according to this exponential, and it's also implied that we really mean the real part of all of that. All right. Recall that the capacitor rule was that the current in a capacitor is capacitance times the time derivative of the voltage across the capacitor. If we have a sinusoidally varying input to the capacitor, then we're going to get like the input current or input voltage or something across it. Then we're going to get a sinusoidally varying output from that. Well, what that means is if we've got a delta Vc, say, of delta Vc naught, so some kind of amplitude, e to the I omega t, then you can calculate the current by taking the derivative of this. The amplitude is a constant, and it just ends up multiplying it by an I omega from what it was before. So that means the current is I omega c delta Vc. Or solving for delta Vc, 1 over I omega c IC. Same thing for an inductor, we get I omega L times the current through the inductor. Now, recall that Ohm's law is V equals IR, or V equals resistance, some constant, times the current. Well, these two relations kind of look like that. As long as we're at a specific frequency, then the terms in front are constants. So we'll define those terms as the complex impedance of the capacitor and the inductor. So capacitor's complex impedance is negative I over omega c. Recall that you could multiply numerator and denominator by I, and then the I squared in the denominator is going to become a negative 1. So that's how the I becomes negative when it moves up. Zc is negative I over omega c, or 1 over I omega c. And the impedance of the inductor is I omega L. The impedance of a resistor is just its resistance. Now, the reason we do this is as long as we're at exactly one frequency, then we can solve these AC circuits involving inductors and capacitors just like we were solving DC circuits involving resistors. We can add impedances in series just like resistors. We can add them in parallel as the inverse just like resistors. We can use voltage divider rules and current divider rules. This is if we've got two impedances in parallel. And we can do things like find Thevenin and Norton equivalents and use Kirchhoff's laws to solve circuits. What are the complex impedances of your circuit if instead you use V naught cos omega t? Instead of that, you use a sine. Well, it's the same. That just is a phase shift. So changing from cos to sine only represents a phase shift, and that had nothing to do with the result of taking these derivatives up here. Moving on with impedance and phasers, the real part of the impedance we would call the resistance, and the imaginary part would be called the reactance. The inverse of impedance is called the admittance. Purely imaginary impedance tells you that the voltage across and the current through a component are 90 degrees out of phase with each other. This is the case for an inductor or a capacitor. In contrast, purely real impedance, like in a resistor, tells you that the voltage and current are completely in phase. For an inductor, the voltage leads the phase of the current. You can think that that'd be the case because it doesn't let the current change instantly. It'll respond with a voltage right away if you try to change the current, and the current catches up over time. For a capacitor, it's the opposite. It can't change its voltage instantly because the voltage depends on the charge on the plates. So if you try to change the voltage on a capacitor, then what's going to happen is you'll first have to lead it with current to build up that voltage over time. So the voltage lags by a quarter of a cycle for a capacitor. You can demonstrate this with phasor diagrams. Phasor diagrams show the complex phasor, so the magnitude and phase being the whole thing in the brackets there, of a voltage or current signal. So it could be a current signal, could be a voltage signal, whichever one that you're showing. It plots them in the complex plane, just like you would plot them if they were polar coordinates. So here's an example of that. Imagine you've got a current, I equals I naught e to the I omega t, so it rotates in time as time increases in the complex plane, rotating counterclockwise. Then if it was an inductor, and this is the current through it, you would have VL is ZLI, and that leads by a quarter cycle. If it were a capacitor, it lags the current by a quarter cycle. Now, if you want to find out what the voltage and current are at any instant, you just take the real part of them. So in the phasor diagram, that represents projecting them onto the real axis. Low pass and high pass filters. Consider this circuit on the left here. We've got an output voltage and taken across the capacitor, and we've got some input voltage there. By finding the impedance of the capacitor and the resistor, we can use a voltage divider to find out the transfer function, which is the ratio of the output to the input voltage. And that goes like 1 over I omega RC plus 1. If omega goes close to 0, then this term goes away and the output is just 1 times the input. Transfer function is 1. If, on the other hand, omega gets really large, so we're at high frequency, then the output approaches 0. This circuit, therefore, is a low-pass filter. It passes low-frequency signals and it attenuates high-frequency signals. We can plot that by looking at the square of the amplitude of this transfer function, square of the square of the transfer function, which would be this. So looking square magnitude, it scales with 1 for low frequencies, and then as omega RC equals 1, we're attenuating to half of the original power. Then it keeps decreasing further on from there. What does the phase do? Phase starts off with no phase shift, and then a 180-degree phase shift as we go to high frequencies, with a 90-degree phase shift at omega RC, at what's called the 3 decibel frequency. We'll see why when we look at decibels. This kind of a plot where we look at the magnitude and the square of the magnitude and the phase versus frequency on a log-log plot is called a Bode plot. Let's consider what happens if we look at this circuit on the right. So if we take the output across the resistor instead. Now the transfer function is almost the same, but we have I omega RC on the top as well. So what this means is that we get the opposite behavior. When omega is really small, then this term goes away and we've just got I omega RC divided by 1, so it's a 0, attenuating low frequencies. If, on the other hand, omega is really large, then the 1 goes away and this scales like just 1. So this is a high-pass filter now on the right. Power dissipation and power storage for oscillating currents. For an AC signal of this form, the time average power dissipation across a resistor, we can just take the average of the power, remembering that we've got to use the real part of the voltage only, and square that divided by the resistance. Then we integrate this with respect to time and divide by the length of one cycle. Calculating this out, remembering that the square of a cosine over an entire cycle has an average value of 1/2, we get 1/2 V naught squared over R. For reactive elements, capacitors and inductors, the instantaneous power storage rate would be the real part of the current times the real part of the voltage. The time average power storage in capacitors and inductors in response to an AC signal is 0. So that's because half of the cycle you're putting energy into the elements, but during the other half of the cycle, you get it back. Now's a good time to bring up what an RMS is. So the RMS of a value is the root mean squared of itself. So the root of the average value of the square of the thing you're finding the RMS of. So if you've got a voltage signal of V naught cos of omega t, then the RMS voltage would turn out to be V naught over root 2, making use of the calculation of the average we just did. This is useful because while in amplitude terms, the average power in a resistor is half of the amplitude of the current times the amplitude of the voltage, in RMS values, it's just the product of the current and the voltage. 2.6 decibels and signal level. A logarithmic scale of decibels is used to characterize the relative strength of signals. We define a decibel unit as 1 decibel is 10 log of 10 times the ratio of the voltage to the reference voltage squared. Now, this, you can take the square out and say that it's 20 times log 10 of the voltage divided by the reference voltage. This is always relative to some kind of a reference voltage. So if you want to say that a voltage has or that this signal is a 20 decibel signal, that means that the voltage is 10 times higher than some reference voltage. You always have to know what the reference voltage is. Multiplying the voltage by a factor corresponds to adding in decibels. So 10 decibels is 10 times higher power than 0. 20 decibels is 100 times power than 0. If you want to talk in terms of voltage, then 20 decibels is 10 times higher voltage than 0. 40 decibels is 100 times higher, etc. Decibels are a relative scale. One common choice for an absolute scale in decibel units is dBm, where V0 there is chosen so that the average power is a milliwatt. Average power of 1/2 V0 squared over R is 1 milliwatt. But even this definition requires some specific resistor value. So if a voltage signal, so for one resistor, maybe a voltage of 100 volts is 1 dBm, but for another resistor, maybe a voltage of 2 volts is 100 dBm. You have to know on the specific resistor value. We're going to skip the Fourier transform section. Not that it's not good stuff, just we don't have time to cover absolutely everything in the course, and this is a bit of a standalone section. But if you're taking 3W or you're interested in signals and systems, then you should go over this section. It's useful. It'll help you draw your courses together and understand electronics and signals at a higher level. 2.8, Resonant Circuits and Bandpass Filters. Let's look at this RLC circuit. RLC because it's got a resistor, an inductor, and a capacitor, RLC. Now let's talk about how this would behave. By using complex impedances, you can calculate out that its transfer function looks like this. And if you have a look at this thing, then we've got a numerator that goes like frequency squared. We've got a denominator that goes like a sum of a constant term after we take the square through, some frequency squared terms, and a frequency to the power of 4. So if the frequency is really low, then the denominator goes like a constant and the numerator goes like frequency squared, so the whole thing goes towards 0. If the frequency is really, really high, then the denominator goes like frequency to the 4, the numerator goes like frequency squared, and the whole thing goes to 0. But somewhere in between, it doesn't go to 0 and reaches a maximum value. Plotting this out, we find that the relative voltage squared, the square of the transfer function, is 0 at the beginning, like we said, 0 at the end, like we said, and then somewhere in the middle, it reaches a maximum. This middle point is called the resonant frequency. It turns out that it's at 1/root LC. It depends on both the value of the inductor and the capacitor, but not actually on the value of the resistor. We'll see what that does in a minute. Now, let's look at this a bit qualitatively. When the frequency is really low, then the inductor doesn't have a very strong response, so low frequencies just pass right through inductors, but they get stopped by capacitors. The capacitor doesn't let low frequency current go through this. Imagine the extreme case of DC current. It goes right through the inductor like it's nothing, and then completely is stopped by the capacitor in the long run, so that there's no voltage that shows up on the output. In the absolute high frequency, something the opposite of that happens, where the capacitor is like a short, but the inductor stops any high frequency signal from going through it. In other words, it carries all the voltage across itself, meaning there's no voltage on the output. Somewhere in the middle, at resonance, the inductor and the capacitor completely cancel out, and this entire branch behaves like a short circuit, so that all of the voltage goes through. There's not even a phase shift at that point. Looking at the phase components, at low frequency, the output is positive pi phase shifted. At high frequency, the output is negative pi phase shifted. But at the middle, it goes right through. So omega naught, 1/root LC, is called the resonant frequency of the system. Now we see what R does. The width of the peak depends on the value of R. For a larger resistance, we have a broader peak. We'd call that a less sharp resonance. But for a narrower peak, we get that when we have a very low resistance. So the height of this peak on this plot, because we're looking at the relative voltage, doesn't change if you change the R value. What R does is it changes the width of this peak. This circuit's also a filter in that it stops some frequencies from going through and only allows certain frequencies through. Now, it doesn't let high frequencies through, it doesn't let low frequencies through, it lets some narrow band of frequencies in the middle through, and so this is called a bandpass filter. bandpass filter. There's another kind of filter called a notch filter, which is the opposite of this. So if we were to change this around so that maybe we took the output across the inductor and capacitor together and then had the resistor up at the top, this would behave like a notch filter then, where it allows all the frequencies except the ones in some narrow range. The bandwidth of this is called the full width at half maximum in the power spectrum. So if we look at this curve and we were to say, what is the width of this when we're at half of the maximum, which is 0.5? That would be the full width at half maximum. What are the units of the full width at half maximum? Well, it's a width, right? So we look at the x-axis, and the x-axis is in frequency, so the full width half maximum is measured in hertz. If we take the resonant frequency, the maximum frequency here, which looks like it's around 10 for this picture, and we divide that by the full width half maximum, then we come up with an important quality of the resonance called the quality factor. The quality factor depends on the resistance value. It depends on the dissipation value of the circuit in relation to the amount of energy stored in the circuit. The lower the resistance, the higher the quality factor. You can see that from our definition of frequency divided by the half width. If we lower the resistance, then this gets narrower, and we have a sharper resonance, higher quality factor. Higher quality factor filters filter a more narrow range of frequencies. Quality factor is also called Q factor, or just the Q. Another definition is that it's the ratio of 2 pi times the peak energy stored to the power dissipated at resonance, just like in a mass spring system. You may have seen that in second year. Now, this is another definition of the quality factor. Does that mean that you have to know which definition we're using when we talk about quality factor? No, actually, the two definitions turn out to be equal. This is useful if you're doing experiments, because often it's much easier to measure one measure of the quality factor than it is to measure another one, and you can use that to get information about the rest of the system. It turns out that quality factor and these calculations don't work so well unless there's a sharp resonance. So if you calculate that the quality factor is about 10 or higher, then you can be reasonably confident that the two definitions are equal. If the quality factor is too low, then you may find some variations between them. Like if you calculate a quality factor less than 1, you can't rely on a lot of this stuff. Like the full width at half maximum doesn't make a lot of sense for really low quality factors. Section 2.9, Understanding the Oscilloscope. Now, this is one of those great application sections that shows up in the book. What we want to take away from this is how oscilloscopes could work. The oscilloscopes that you have in the lab are digital oscilloscopes, digital. They don't work exactly the same as this anymore, but their controls would suggest to you that they do. And if you find yourself with an older analog oscilloscope, then you'll know exactly how it works. What I suggest you do is follow through the picture, read the description, go by the summary if you like, and then take the time next time you're in the lab to see how the controls line up with these, and picture how the oscilloscope could be working to tell you what the signal that you're looking at. Exercise 2.9. Determine the output function V0 over V in magnitude squared, so the square of the transfer function, for a high-pass filter made from a single capacitor and resistor. Just to remind you, this is what the high-pass filter configuration is. So earlier on we introduced this and then we calculated it for the low-pass filter, but we didn't explicitly calculate it for the high-pass filter, so go ahead and do that now. All right, using your voltage dividers after finding the impedances, we come up with a transfer function of R over R plus the impedance of the capacitor. Calculating this out, you can come up with the square of this as 1 over 1 plus 1 over omega squared R squared C squared. All of these are in the denominator here. Remember that when you square a complex number, that it actually means you take the complex number multiplied by its complex conjugate. Complex conjugate negates the imaginary terms no matter where they show up in the equation. So here they were in the denominator, doesn't matter, still switches all the negatives to positives and positives to negatives for imaginary terms. Exercise 2.10. Determine the output voltage characteristic for the circuit with an inductor in place of a capacitor in the low-pass filter. So here was our low-pass filter. We put an inductor in place of this capacitor. What's the transfer function going to be? Give it a shot. Here we go. So behaves just like this. Voltage divider using our inductor, and there's our transfer function. Now, as a bit of a follow-up question, what is this? Is this a filter? And if so, is it a low pass or a high pass filter? Give it a shot to think about that. Well, looking at this, if frequency is really low, then the R term dominates in the denominator and the numerator goes to 0. So this attenuates low frequencies. If frequency is really high, the R term is dominated by the I omega L, and we've got just a 1, meaning that this has a transfer function of 1 for high frequencies and goes towards 0 for low frequencies, so it's a high pass filter. That could make sense by thinking about the idea that the capacitor and inductor are kind of like opposites. So if you were to replace the capacitor with an inductor and this was a low pass filter before, it's a high pass filter now. Exercise 2.9 dealt with the high pass filter shown in 2.18b. Determine the frequency omega at which the output is 3 decibels lower, 10 decibels lower, and 20 decibels lower than the frequency going to infinity value. Make a Bode plot for this circuit. So this is going back to the one that we just did, where we found the transfer function for this high pass filter. And what you have to do now is crunch some numbers and figure out where is it that we're going to have a 3 decibel lower signal, 10 decibel lower, and 20 decibel lower signal than the high frequency value, which is a 1. Okay, so if you solve that this equation is, so we want to know where this is going to give us certain values. The best way to do that is to first solve it for the frequency. Then we say, well, 3 decibels lower means that the 3 decibels is equal to 10 log 10 of this voltage ratio. That's how we define the decibel signal, the decibel unit. So if it's 3 decibels lower, then it's negative 3 decibels output relative to the input. All right, that tells us what we need for V naught over Vi squared. We find by dividing by both sides by 10 and then raising to the power, taking that as the exponent on a 10, we get that V naught over Vi squared has to be 0.5. Substituting that in here, we find that a frequency of 1 over RC is going to give us a 3 decibel attenuation. Repeating for the next ones is pretty trivial at this point. Omega is 1 over 3 RC for a factor of 10 attenuation, and a factor of 100 attenuation is omega is 1 over 10 RC. Plotting this, we can talk about the 3 dB frequency. 3 dB frequency is a characteristic of where the filter starts to cut off. Some students will just say, okay, I want to design my high pass filter to stop frequencies that are lower than, let's say, 100 hertz. And if they pick 100 hertz there, they solve for the RC that gives you an F of 100 hertz, and then just design it like that. But does that completely attenuate frequencies that are at 100 hertz? Well, no. It attenuates them so that they've got a 3 decibel lower power. 3 decibel lower power means that the power is just a half of what it would be in the passband. So if you want a stronger attenuation, you need to move your 3 dB frequency. By adjusting the value of R and C, you can change what where this frequency is and how your filter is going to behave.